Alright, let's look at this problem. We're constructing influence lines still. We're going to construct it for the moment at C. So here's our C connection. And just like we did in previous problems, we're going to cut the structure here at C to find the internal moment. And we have to decide whether we work the left side or the right side. I'm going to work the left side. I think that's going to be a little easier to do. So if I do work the right side, what do I have to find first? I got to find my reaction at A. So again, I'll get double duty out of this diagram and go ahead and just define AY and BY. So let's find our reaction at A due to our unit load operating at some position X. So how do we find the reaction at A?
Moments at B.
Take moment at B. And you guys know by now that I like right-hand rule for my sign convention. So we'll sum the moments at B and make sure it's in equilibrium. So what is the moment of this force about B? Well, if it's at... I'm sorry, go ahead. Oh, since the force is located from the right-hand side at some position, let's say X, then what is this distance?
10 minus X.
10 minus X. So now I'll know that about B, the unit load creates positive moment. There's the force. And the moment arm would be 10 minus X. And then I'll have my reaction at A, which is going to create negative moment about B, and it'll have a moment arm of 10. So solve for AY. And it looks like you're going to get 1 minus X over 10. And that makes sense. We can always check it. So when X is 0, which means my unit load is right above A, the reaction at A is 1. When I go all the way over to 10, 10 over 10 is 1, 1 minus 1 is 0, so when the unit load is right here above B, AY is 0. Now what happens when it moves to the right? Let's say go all the way to 15, so I got 15 divided by 10 is 1.5, and 1 minus 1.5 is negative 0.5. So now A has turned over and is holding point A down, which makes sense. It's kind of like a seesaw now. So you put the big kid here on the right hand side, the left side is going to go up in the air. So you got to balance it. So that seems to work. So now let's go back and find the moment at C. So I'll draw a free body diagram for that. So there's my chunk of the beam. We'll put our reaction that we just found. So we know AY, I assumed it was up, and has a value of 1 minus X over 10. I'm looking for the moment at C, so I'll assume positive bending moment at C. And I'll go ahead and in this case, I'll look for the unit load operating on that free body. Oh, I forgot the dimension here. This is 5. So this one will be good when the position of the unit load is between 0 and 5. But what happens if it's greater than 5? Well, in that case, it's moved off the free body diagram. I still have my moment at C, which I'm trying to find. I still have my influence line for the reaction at A, and this thing is still 5 feet, except the unit load has now moved over here. It's operating between 5 and 15, which is not on this free body. So I'll label this one as being valid from 5 to 15. So these are pretty simple free body diagrams to solve. Start up here with the first one. So again, we'll sum moments. This time we'll sum them at the cut that I've made. Make sure it's in equilibrium. So my moment about C is positive. the moment created by the unit load about C is also positive. And what's the moment arm for that? What's this distance right here? 5 minus x, that's right. And then I have my reaction creating negative moment, and that's 1 minus x over 10, and it has a moment arm of 5. So I just have a little work to do here. So let's see, MC is equal to, all right, let's see, I've got a positive 5 here, and I'm subtracting 5, so that cancels. I have a negative x here, and then I have a positive x over 10, 5x over 10. So negative x plus positive half x gives me negative x over 2. And throw that to the other side of the equation, I get positive x over 2. That may not have been the most eloquent way of doing that.
Can I ask a question?
Sure.
Why isn't it on the other one you just found a shear, but now that you're finding a moment?
Well, the question asks, what's the influence line for moment?
Oh.
Right? The previous one was, what's the influence line for shear? That's okay.
Gotcha.
So now, let's do the same idea, except we'll now do it for the second free body. And in that case, our unit load has left this free body diagram. So our moment is still the same, MC. We still have the negative moment created by, oops, I didn't mean to put that 1 there, but it won't hurt anything. This is still the reaction with the moment arm of 5. But we just don't have this to deal with anymore, so that term is out. So I'm sorry about that 1 there. It doesn't really hurt anything. But I end up with 5 minus x over 2. So I throw it to the other side of the equation. My m sub c now becomes 5 minus x over 2. And all I have to do now is plot those two equations. So let's create a quick axis. Our ordinate is going to be the moment at C. And the x-axis, I think it's called the abscissa, I don't know if I can say that right, will be our position. And we'll look for 5, 10, and 15. So between 0 and 5, the function is x over 2. So when x is 0, we have 0. When x is 5, you put 5 in there, you get 2.5. I'll just write it as 5 over 2. And of course it's linear. Now from 5 to 15, which are these remaining 5 feet, what do I have? Well, when I put 5 in here, I get 5 minus 5 over 2, which is 5 over 2. So it matches. And then if I go all the way to the extreme at 15, what do I get? Well, let's not do that. Let's go to 10. So 10 divided by 2 is 5. So 5 minus 5 is 0. And then I go to 15. I get 15 divided by 2, which is 7.5. So 5 minus 7.5 is minus. So I didn't quite get it to scale, but I think you get the idea. So this would be at minus 5 over 2. You don't have to draw this back up like that, but I might help you visualize it a little better. So what does this mean?
We're done.
Well, we're done with the problem. That's one thing. That is one objective. We have completed the problem. A second objective, kind of more of a structural engineering sense, would be I'm on my unicycle. Where do I go to create the largest positive moment at C? So you go to the largest positive value, which is here, which is at x equal 5. So I ride my unicycle to 5 feet. I'm creating the maximum positive moment at C. Where do I go to create the maximum negative moment? 5 Find the largest negative value. There tells me the position, 15. So I ride all the way out to the end. I'm now creating maximum negative moment at C. Any other questions? Okay.